Good morning, dear students. Now we shall see how the potential energy approach is useful to determine the element stiffness matrix and load vectors. We know that the strain within the element is constant. When you take a one-dimensional element connecting two nodes, the strain within this one-dimensional element is constant. The reason is, you know that epsilon equals to B into Q. What is B here? It is the strain displacement matrix. The strain displacement matrix depends on the length of the element. Because the length of this element is constant, so B is constant. And what is Q? It is the element displacement vector. Therefore, the nodal values are also same or constant for this element. Hence, the strain within this element is constant. When strain is constant, stress is also constant. The reason is, for all the one-dimensional problems, stress by strain equals to Young's modulus. For a known material, E is constant and strain is also constant, therefore stress is constant. This is the reason why we can understand that the strain within the element, within the one-dimensional element is constant. When strain is constant, stress is also constant. Right? The stress within the element denoted by sigma equals to EBQ, because epsilon equals to B into Q. B is the strain displacement matrix and Q is the element displacement vector. Okay. Now, the expressions U equal to NQ, epsilon equal to BQ and sigma equal to EBQ, if you observe carefully, U equal to NQ, the expression U equal to NQ relates the displacement with the displacement vector, and the expression epsilon equals to BQ relates the strain of the element with the displacements of the nodes, and the expression sigma equals to EBQ, if we observe, so here this expression relates the stress within the element with the nodal displacements of the element. Okay. Now, we substitute so these expressions in the potential energy of the elastic solid and see how the element stiffness and load matrices are derived. Okay. We substitute these expressions in the potential energy approach and see how the element stiffness and load matrices are derived. Okay. Now, we know that the potential energy of an elastic solid pi equals to the strain energy and work potential. The strain energy we can determine when deformation takes place. When the deformation takes place, when the solid is under the action of a set of forces. For example, I take a bar of uniform cross section like this. A bar of uniform cross section is like this. It is subjected to an external force, say F, right? Its self-weight is acting on the entire volume of this object. Self-weight is the body force. Now, the same solid is also under surface traction, say T. Now, what happens? Because it is under the action of the surface forces and the body force, deformation takes place. Right? When deformation takes place, you can determine the strain energy of the elastic solid. I tell you an example. So, take a compression spring, keep one and fix it. Now apply a push on the spring. if you apply a push on the spring, what happens now? The spring undergoes compression, right? Now the spring is in deformed state. If you remove the force, then what happens? The same spring comes back to its original shape, because energy is stored in the spring in the form of strain energy, right? This strain energy is due to internal forces. Hence, you can determine the strain energy of the solid using this expression. So, how you determine that we see? So, here the formula for determining the strain energy is 1 by 2 into integral of sigma transpose into epsilon A into dx, where capital L is the length of the solid. That I explained carefully here. Now what I do is, I take a bar of uniform cross section. This is a bar of uniform cross section. What is A? The cross section area of the bar. Now L is the length of the bar. Okay. Now E is Young's modulus of the bar. Assume that this bar is subjected to an axial force F. Okay. Now, what is my interest? My interest is to determine the strain energy of this elastic solid. Okay. Under the action of this force, this bar undergoes deformation. Right? Now, due to deformation, what happens now? The energy is stored in the object in the form of strain energy that I determine. How I determine? See here. So here, if I consider an infinitesimal element of thickness dx, distant x units from the fixed end, what is the energy stored in this infinitesimal element? If you determine an expression for the strain energy stored in this element, you can also use it to determine the strain energy stored in the entire elastic solid. How? That we see now. Now, here, the volume of this infinitesimal element denoted by say dV, which equals to A into dx, where dV is the differential volume, or you say volume of the infinitesimal element, where the cross-section area is same throughout the length of the bar. Therefore, it is constant, only x is variable. Okay? Now, when you plot a stress strain diagram here, now the stress and strain, if you plot taking strain on x-axis and stress on y-axis, within the limit of proportionality, stress is directly proportional to strain. Hence, what happens now? You get a straight line like this. You get a straight line like this up to proportional limit. Okay. Now, when I draw a line vertically like this, this is right angle, this is right angle. Therefore, how this triangle appears? It is a right angle triangle. Okay. Up to proportional limit I am taking, because when you load the elastic solid up to proportional limit, after removing the force, what happens? It comes back to its original shape. Right? Hence I can say it is in the state of elasticity. Therefore, within the state of elasticity, I determine the strain energy of the elastic solid. How? See here, when I take the area of this triangle equals to half base into height. Half into, what is base? It is epsilon. And what is height? It is sigma. So therefore, the area of this triangle equals to half into epsilon into sigma. Okay. Now this half epsilon sigma gives me the strain energy per unit volume. The strain energy per unit volume. Okay. Now, the strain energy of this infinitesimal element distant x from the fixed support I determine. How? Multiplying this half epsilon sigma by the differential volume dV. Therefore, if I multiply, what I get? 1 by 2 into sigma into epsilon into A into dx. This is the expression for determining the strain energy of the infinitesimal element. Okay. Now, if I want the strain energy of this entire solid, then what I have to do? I have to integrate this over the length of the solid. Therefore, the strain energy of the elastic solid US equals to integral of half into sigma into epsilon into A dx. Right? Integral over the length of the solid. This is the expression, we use. This is the expression which we use to determine strain energy of the elastic solid. That is what I have written here. Right? You need not worry about this transpose because for one-dimensional problems, sigma transpose is same as sigma. The reason is, if we observe the stress matrix sigma, how many components it consists of? In fact, the stress matrix sigma is a column matrix consisting of sigma xx, sigma yy, sigma zz, tau xy, tau yz and tau zx. But for one-dimensional problems, sigma yy is 0, sigma zz is 0, tau yx is 0, tau zx is 0 and tau zy is also 0. Therefore, sigma is simply sigma xx. Hence, sigma transpose is same as sigma. You need not worry. Right? So, what is the expression for determining the strain energy of the elastic solid? 1 by 2 into integral over the length of the solid sigma transpose into epsilon A dx. Or you can write 1 by 2 into integral over the length of the element sigma into epsilon A dx. What is variable here? X is variable. For one-dimensional problems, we take only one coordinate, that is x. Understand? This is how one can determine the strain energy of the elastic solid. And coming to the work potential. Why we determine the work potential? Because the total potential energy of the elastic solid pi is the sum of the strain energy of the elastic solid and the work potential. What is work potential? Work potential is due to work done by external forces. What are the external forces here we are considering? As I said, we consider the concentrated force, we consider the surface traction and also we consider the body force. Okay, so firstly we see the work done by the body force. Work done by the external forces is considered negative and work done by internal forces is positive. Okay, so what are the internal forces here? The forces that are set up against the external forces. The forces that are set up inside the body against the external forces. So the work done by the internal forces we have determined, right? That is the strain energy US. We have the expression for determining US here, and now we shall see the work done by external forces. Firstly, we consider the body force. The body force, work done by the body force, we can determine using this formula. So, minus of integral of U transpose FA into dx. Right? Now here, why we use minus? Why we use minus? Because work done by the body force is negative. Okay? Or you avoid minus here, later you can put minus when you determine the total potential energy. You can avoid putting minus here and later you can put minus when you determine the total potential energy of the elastic solid. Now, so how you get this expression? That is the question. How you get this expression? That is the question that we see now. Now, I take a bar of uniform cross section. Okay. L is the length of the bar. A is the cross sectional area of the bar. And E is the Young's modulus of material. What force we are considering here? The body force. Now, where F is the body force per unit volume. It is distributed over entire volume of the solid. F is body force per unit volume. We have to understand. Body force per unit volume. Per unit volume. Body force per unit volume. Okay. Now, where this body force is acting, is acting on the entire volume of the object like this. Self weight is the example. Okay. Now, so what is the total body force acting on this object? That is the question. Okay. The total body force acting on this is simply F A into L. What L represents here? The volume of the object. What is the cross-sectional area of the solid? The body force per unit volume into volume of the solid gives you body force acting on the solid. Okay, now to derive the expression, what we do is we consider an infinitesimal element. I draw the figure again. I take the same solid, I draw it to some enlarging scale like this, right? I consider an infinitesimal element of thickness dx, distant x units from the fixed support, right? This is the orientation of the coordinate axis x. Where is the origin? Here. Because the cross-sectional area is same throughout, then the volume of this element, the differential volume of this infinitesimal element dV equals to A into dx. Okay, now what is the body force of this infinitesimal element? It is simply F into AdX. F AdX is the body force of this infinitesimal element. Okay, now what done by this body force I want? How we write is simply the displacement into the body force. We know that the displacement U equals to N1 Q1 plus N2 Q2. Okay. What are N1 and N2? They are the shape functions. For one-dimensional problems, we derive the shape functions N1 and N2 in terms of the coordinate J, the natural coordinate J. N1 equals to 1 minus J by 2 and N2 equals to 1 plus J by 2. Okay. Now, this if you write as the product of two matrices, a row matrix with elements N1 and N2 into a column matrix with elements Q1 and Q2. Okay, now how you write this equals to N into Q, where N is the shape function matrix. It is a row matrix having the elements N1 and N2, and Q is the element displacement vector. It is a column matrix having the elements Q1 and Q2. Understand? Now, so when you implement the finite element method, what is the basic idea? Our basic idea is, to divide the given solid into a number of finite elements. I take, for example, two elements here. from here to here this is one element, and from here to here this is another element. Okay? Therefore, what are the nodes here? This is the first node, say 1. This is the second node, say 2. This is the third node, say 3. We have 2 finite elements here. Right? Now, tell me, this is the length of the first element. Length of the first element, say 1, L1. Okay? Length of the first element. Now, the work done by the body force FA dx, how you get, multiplying this FA dx with U. With U. What is U? N into Q. What is the size of N here? 1 by 2. And the size of Q is 2 by 1. Ultimately you get 1 by 1. Right? We can also write this NQ as Q transpose into N transpose, because the size of Q transpose is 1 by 2 and the size of N transpose is 2 by 1. You get 1 by 1. In this particular case, you can write NQ as Q transpose into N transpose. In place of NQ, I write Q transpose into N transpose for my convenience. Okay. Therefore, the work done by the body force of the infinitesimal element is F A dx into Q transpose into N transpose. This is the expression to determine work done by the body force of the infinitesimal element. Understand? Okay? Now, if you want the body force of the entire finite element, say I take element number 1, then what you have to do? You have to integrate this over the length of the element. I told you in the previous class, if E denotes the element number E, so here I take, it is N circle. If E in a circle represents element number, right? The first node is denoted by say E, then the second node is E plus 1. If E in a circle represents element number, the first node is denoted by E and the second node is denoted by say E plus 1. Right? With this notation, what I do is I write here the expression to determine the work done by the body force of the one-dimensional element, integral over the length of the element E, Q transpose into N transpose into F A into dx. What is F? Body force per unit volume. Right? F is constant for each finite element. Understand? So this is what we had in our slide. This is what we had in our slide. See here. Okay? U transpose into FA into dx. What is U transpose? U transpose is simply Q transpose into N transpose. That is what I have written in my expression. Right? Therefore, this equals to integral over for an element, integral over the length of the element Q transpose into N transpose into F into A into dx. When the solid is divided into finite number of elements, then for each element you have to determine the work potential due to the body force. Then you sum up. Then you get the work potential of the body force of the entire solid. Okay? Then we write integral over the length of the solid. We have to understand carefully. For each element, if you determine what is the expression, the work, for the work potential due to the body force, the work potential done by the body force F equals to integral of Q transpose into N transpose into Fa into dx. Integral over the length of the element. Work done by the body force is negative. When the one-dimensional solid is discretized into a number of finite elements like this, the work potential due to the body force in each element you have to determine. How many elements are here? There are 5 elements. For first element, using this expression, you have to determine work potential. For second element, you have to determine work potential using this expression. Right? Work done by the body force, concerning first element, you have to determine. Take second element, then work done by the body force, you have to determine. Determine work done by the body force considering third element, then work done by the body force considering fourth element, work done by the body force considering fifth element. Then you sum up. Then you get work done by the body force of this elastic solid. Therefore, work done by the body force of this entire elastic solid, how you get? This sum of the work done by the body force of the element E, where E varies from, in this case, say 1 to 5. If there are n number of elements, then how you write the sum of work done by the body forces of all the elements, right? Where I varies from 1 to n. Okay. Now the work done by the body force for each element. What is the expression? Integral of the length of the element into Q transpose into N transpose into Fa into dx. If you want for the entire solid, if L is the length of the solid, then the work done by the body force of the entire solid is integral over the length of the entire solid. Understand? Integral over the length of the entire solid into U transpose into Fa into dx for the entire solid. Or you can write like this. When you write like this, what you have to do? You have to determine the work done by the body force of each element. If there are 5 elements, for all the 5 elements, you have to determine work done by the body forces. Then you sum up. You get work done by the body force of the entire solid. Okay? Now, we know how to derive this expression. We know how this expression is obtained. Okay? Next. So coming to work potential due to traction, surface traction. Right? Surface traction is denoted by capital T. Surface traction is denoted by capital T. Okay? Now, so here, the work done by the surface traction T equals to minus integral of U transpose into T into dx. Now to integrate U transpose T dx over the length of the element. Over the length of the element. Sorry, over the length of the solid. Again, as I said, take a bar of uniform cross section and apply the traction here like this. Surface traction, T is the traction. How do you define traction? Traction we define as the force distributed per unit length. Per unit length. Understand? Right. So why you take the force distributed per unit length? Because the perimeter of this member is constant everywhere. In fact, this traction is applied on the surface of the object. What is the surface area? The surface area is simply, the surface area is simply pi d into L. What is pi dl? If d is the diameter of this, solid and L is the length of the solid, then the perimeter of this solid is pi d, because d is the diameter, into length of the solid gives you the surface area. Okay. Here pi d, perimeter is constant through the length of the solid. Hence we can define here in one-dimensional problems T as the force per unit length. The force per unit length. How you get this expression? As I explained, in the previous case. Okay. Now, what is the traction? Total traction, acting on this solid simply T into L on the entire solid. T into L. What is the length of this solid? Okay. Now, if you consider an infinitesimal element of thickness dx, distant x from the fixed end, Understand? So what is the traction acting on this infinitesimal element? I draw the infinitesimal element to enlarging scale. This is the traction T. What is the thickness of this element? Dx. Thickness of this element is dx. Therefore, the traction acting on this surface is T into dx. Simply. The surface traction on the infinitesimal element is Tdx. Right? Now, the work done by this traction, you have to determine. That is the work potential. How? Multiplying this by the displacement u. Therefore, the expression is u into T dx. But we know that u equals to nq. Right? N is the shape function matrix. It is the row matrix having the elements n1 and n2. n1 and n2 are the shape functions. And q is the element displacement vector having the elements q1 and q2. It is a column matrix. Right? In place of u, you can write nq, or you can write q transpose into n transpose. Okay. Now, so what you write? Therefore, q transpose into n transpose into t into dx. Understand? Because u equals to n1 plus q1 plus n2 into q2, you can write u as u transpose. U as u transpose. Understand? U as u transpose. So therefore, how you get the expression? Now, integral of u transpose into t into dx. In place of u transpose, you can write q transpose into n transpose, right? And you get the integral of q transpose n transpose into t into dx. This is how we derive this expression. Next, what are the other forces? The other forces are simply concentrated forces. Concentrated forces are denoted by, say, Pi. How I understand Pi? Pi is the concentrated force acting at node I. This is how I understand. Again, I draw a figure. I have a one-dimensional bar, a bar of uniform cross section. Okay. Now, one force is acting here at this point, another force is acting here at this point. This is the force say P1 and this is the force say P2. Where they are acting, I say P1 is acting at node 1, and P2 is acting say at node 2. Or to understand more clearly, I say, this is the force P2 and this is the force P3. P2 is the force acting at node 2 and P3 is the force acting at node 3. This I say node 1. Now it is very clear. Without confusion you can understand. Right? Now from here to here this is first finite element. For which what is the first node? Node 1. And what is the second node? Node. And from here to here this is second finite element. For the second finite element node 2 is first node and node 3 is second. Now how I understand P2? P2 is the concentrated force acting at node 2 and P3 is the concentrated force acting at node 3. Therefore, I can use the symbol Pi to denote the concentrate force acting at node I. Okay. Now, what is the work potential due to P2 and P3? Because they are acting at nodes, we can obtain the nodal values. Nodal values are given by the finite element method. Right? So what is the nodal value at 2? It is simply Q2. I told you in one of the previous classes. Nodal value at node 3 is simply Q3. Where Q2 and Q3 are the global displacements. Therefore, when you multiply P2 by Q2, you get work done by the concentrated force P2. When you multiply P3 by Q3, you get the work done by the concentrated force P3. Then you sum up. Simply. Then how you get the work done by the concentrated forces P2 and P3 is simply P2 into Q2 plus P3 into Q3. Understand? P3 into Q3. P2 into Q2 plus P3 into Q3. Okay. So here, what UI represents the displacement at node I. That is what I understand. The displacement at node I is simply the nodal displacement. Okay. If I take I equal to 1, then what U1 represents? The displacement of the first node, which is simply Q1. That is what we have to understand. Okay. When you expand this, how you get U1 P1 plus U2 P2 plus U3 P3 and so on so forth. U1, what U1 indicates? The displacement at node 1, that is Q1. Therefore, I write here Q1 into P1. Q1 into P1. Now, what U2 represents? The displacement at node 2. Therefore, I write in place of U2 Q2. Hence, Q2 into P2. Okay. The work done by all the concentrated forces, how you write? Simply the sum of, right, Qi into Pi as I varies from say 1 to n. Hence you can replace the sum of Ui Pi as I varies from 1 to n, you can replace by the sum of Qi Pi as I varies from 1 to n. Okay. Now, the expression for potential energy of the solid is pi, which equals to, I said, the strain energy of the solid plus work potential. Okay. So what is the strain energy? 1 by 2 into integral over the length of the solid sigma transpose into epsilon A dx. Right? And work potential is negative. same. Therefore, I put minus here. So minus integral over the length of the solid into U transpose into F A dx. What this indicates? What this indicates? Which indicates what this term indicates? Which indicates the work potential due to body force. Next, minus integral over the length of the solid U transpose T into dx. What this indicates? This indicates the work potential due to traction. Minus the sum of Ui Pi. What this indicates? The work potential due to concentrated forces. Okay. So this is how one can determine the total potential energy of a solid. So what we have learned in this particular class, we have used the strain displacement relation, the stress strain relation, and the displacement and nodal displacement relations, U equal to NQ. The displacement and nodal values, an expression relating displacement and nodal values, an expression relating the unknown displacement and nodal values, U equal to NQ. Next, an expression relating the strain and displacement, and an expression relating stress and strain. These expressions we have used to determine the potential energy of the elastic solid. Right? The strain energy of the elastic solid we have determined. The work potential due to body force we have determined. The work potential due to traction we have determined, and the work potential due to external forces we have determined. Then we have determined the total potential energy, summing up the strain energy of the elastic solid and the work potential of the external forces. What are the external forces? Body force, traction, and concentrated forces. And ultimately, we have obtained an expression like this. Okay. In next class, we see what this term results in. What this term results in. What this strain energy term results in. We also see what this term results in. What this term results in. Okay? Right. Thank you. Thank you very much.